Welcome everyone for this new SIPTA seminar, the last seminar of the year. So for the last seminar, we are especially happy to receive Daniel Kuhn, which will speak to us about optimal transport and robust optimization. And to chair this session, I'm very happy to pass on the mic to Matthias Trofas.
Okay, so welcome everybody. It's a really great pleasure to introduce our very distinguished speaker today, which is Professor Daniel Kuhn. He holds the Chair of Risk Analytics and Optimization at the very prestigious École Polytechnique Fédérale de Lausanne, or the EPFL. He's renowned for groundbreaking contributions in the field of optimization and in decision science, and this includes data-driven optimization, developing tractable methods for stochastic and robust optimization problems, and his work essentially enables some more robust solutions for decision-making under uncertainty. And this has many applications, including energy systems, machine learning, finance, business analytics, and many more. And what is really fascinating that is his work bridges highly theoretical advancements with really important real-world applications. So what is also really interesting to our community is his ideas around distributionally robust optimization, which I believe is closely linked to bounded probability or imprecise probabilities. So today, Professor Kuhn will talk about the fascinating interplay between optimal transport and this distributionally robust optimization. I invite you all to engage in what will be a very captivating talk, I'm sure, and a discussion with strong theoretical and practical connections to our community. So please join me in extending a warm welcome to Professor Daniel Kuhn. Over to you.
Thank you very much, Matthias, for the very kind introduction. And it's really a great pleasure to have the opportunity to give this seminar. Especially the last one this year. And I think indeed there is probably very interesting connections between what your society does and between distributional robust optimization, and it would be great actually to get some feedback on each other's work. So I think it's a great opportunity. So as Matthias pointed out, so the goal of my talk will be to show that there is a fruitful cross-fertilization between optimal transport and distributional robust optimization. And in fact, I would like to show that this cross-fertilization goes both ways. So let me start by giving a short introduction into the theory of optimal transport. So consider a random variable xi1 with a distribution p1. And then let's look at the measurable transformation tau. So we can then construct another random variable xi2, which is defined as tau of xi1. Clearly, the distribution P2 of xi2 is uniquely determined by the distribution P1 and by the transformation tau. In order to construct this distribution P2, we need to determine the probability that xi2 falls within an arbitrary Borel set B under P2. And this is the same as the probability that tau of xi1 falls within B under P1. Or equivalently, that the probability that xi1 falls into the pre-image tau inverse of B under P1. So the distribution P2 that is constructed in this way is the push-forward distribution of P1 with respect to the transformation tau. We can now turn the problem around. Given two distributions P1 and P2, there are potentially many transformations tau that push P1 forward to P2. Any such transformation, tau, can be interpreted as a transportation map. So in 1784, Gaspard Monge formulated the optimization problem shown on this slide. This problem seeks the cheapest map for transforming P1 to P2, where the cost of moving a unit probability mass from a point xi1 to the point tau of xi1 is quantified by a cost function C. Intuitively, one may interpret the distributions P1 and P2 as two piles of sand, and the cost function C as a distance function in the xi1 space. And then the infimum of Monge's optimal transport problem quantifies the minimum cost for converting the pile P1 to the pile P2. Now, unfortunately, Monge's optimal transport problem is not guaranteed to be solvable or even feasible. The problem is that a transportation map tau moves all the probability mass from a given origin to the same destination. And this is too restrictive. A better concept is that of a transportation plan, which allows for mass splitting. So specifically, a transportation plan pi can split the probability mass at a given origin and transport it to multiple destinations. So mathematically, a transportation plan pi represents a coupling, and that is a joint distribution of the random variables xi1 and xi2 with marginals p1 and p2 respectively. That is, integrating pi along xi1 yields the distribution p2, and integrating pi along xi2 yields the distribution p1. So in 1942, Nobel laureate Leonid Kantorovich formulated the optimal transport problem that is shown here, which aims to find the cheapest transportation plan pi for morphing P1 into P2. This problem relaxes Morph's optimal transport problem, which optimizes over the smaller set of transportation maps. And here we're more general because we allow for mass splitting. So mathematically, Kantorovich's problem is much nicer. It is always feasible. And if the cost function C is lower semi-continuous and bounded below, then it is also guaranteed to be solvable. Computationally, the problem is also much nicer than Morph's problem because it constitutes a linear program, while Morph's problem is non-convex. In 1969, then, Leonid Wasserstein used optimal transport theory to study a class of probability metrics. So specifically, for some number p larger or equal to 1, he considered an optimal transport problem whose transportation cost function C is the pth power of some metric on the Xi space. Very often in applications, this metric is induced by some norm on the Xi space, indeed. And one can then show that the pth root of the optimal transport problem's optimal value constitutes a metric on the space of probability distributions. And in honor of Wasserstein, this probability metric is referred to as the pth Wasserstein distance. So computing the Wasserstein distance between two discrete distributions is tractable, as it simply requires the solution of a tractable linear program. Unfortunately, however, tractability is lost if at least one of the two distributions fails to be discrete. So indeed, one can show that computing the Wasserstein distance between a continuous and a discrete distribution is sharply hard already in the simplest imaginable setting. And that is perhaps when P1 is a uniform distribution on the unit hypercube in d dimensions, and when P2 is a discrete distribution with only two atoms. So here is a proof sketch of this result. So a knapsack polytope in RD is the intersection of the d-dimensional unit hypercube and an arbitrary half space. Now, any half space can be characterized as the set of all points that are closer to 0 than to some other point W. And we denote the knapsack polytope corresponding to W by P of W throughout this proof. Now, it is well known, that's a result by Dyer and Fries from 1988, that computing the volume of the knapsack polytope P of W is a sharply hard problem. Okay, let now P1 the continuous uniform distribution on the hypercube in RD, and let P2 be the two-point distribution that assigns probability alpha to 0 and probability 1 minus alpha to the point W. To compute the Wasserstein distance between the continuous distribution P1 and the discrete distribution P2, we need to find the optimal transportation plan that maps a fraction alpha of the uniform distribution to 0 and a fraction 1 minus alpha of the uniform distribution to W. Now here's a video, and the video visualizes the transportation plan for different, so the optimal transportation plan for different values of alpha. The part of the uniform distribution that is moved to 0 is colored in turquoise, and the part moved to W is colored pink. The Wasserstein distance between P1 and P2, which is shown on the right chart, is minimized if all points that are actually closer to 0 than to W are all moved to 0. So the amount of mass that is transported to 0 in this case exactly coincides with the volume of the knapsack polytope P of W. Now assume for the sake of argument for a moment that it is easy to compute Wasserstein distances between uniform distributions and two-point distributions. In this case, one could efficiently minimize the Wasserstein distance between P1 and P2 over all probabilities alpha between 0 and 1. And thereby, one could actually efficiently compute the volume of the knapsack polytope P of W. However, this contradicts the hardness result by Dyer and Fries, and therefore this implies that computing the Wasserstein distance between P1 and P2 must indeed be sharply hard. Okay, so generically, it is hard to compute Wasserstein distance between non-discrete distributions. When the transportation cost is equal to the squared Euclidean distance, however, the Wasserstein distance is sometimes available in closed form. And whenever such a closed form expression is available, it is based on Brogniet's theorem, which is shown here. And this theorem provides an elegant characterization of the optimal transportation map tau star that is optimal in Morph's optimal transport problem. So Brogniet's theorem asserts that a map tau star is optimal if and only if it satisfies a feasibility condition and an optimality condition. The feasibility condition is simple. It just requires that tau star must push P1 forward to P2. That's clear. The optimality condition, on the other hand, is that tau star must be representable as the gradient of some convex function phi. So the optimality condition is quite intuitive in one dimension. In this case, the gradient of any convex function is monotonically non-decreasing. Now, Brogniet's theorem in this case just states that tau star is optimal if and only if it is feasible and non-decreasing. Hence, if tau star moves mass from a point x to a point y, then the mass from any point to the right of x must be moved to a point to the right of y. And in one dimension, it's indeed elementary to verify that any map that would violate this monotonicity condition cannot be optimal. Okay, so consider now two random variables, xi1 and xi2, with distributions P1 and P2 respectively, and assume that xi2 is a positive semi-definite affine transformation of xi1. This means that xi1 can be written as xi2 can be written as A times xi1 plus B, where A is a positive semi-definite matrix and B is a vector. Now let's denote this affine transformation by tau star. Clearly, any positive semi-definite affine transformation is the gradient of some convex quadratic function. So therefore, we can now use Brogniet's theorem to conclude that tau star, the tau star defined here, must be the optimal Morph map for transporting P1 to P2. Now, even more, the matrix A and the vector B of this optimal Morph map can uniquely be expressed in terms of the mean vectors and the covariance matrices of the two distributions P1 and P2. Indeed, an elementary calculation shows that the A matrix can be expressed as admittedly somewhat complicated formula in terms of the covariance matrices sigma 1 and sigma 2, while the B vector can be expressed in terms of A, which we already have determined, as well as in terms of mu1 and mu2, the two mean vectors. All of this implies that the squared 2 Wasserstein distance between P1 and P2 can be obtained by substituting the optimal Morph map, tau star, into the objective function of the optimal transport problem. Now, this means we have to solve an integral, but as the integrand of this objective is a quadratic function of xi1, the integral can be computed analytically in terms of the first and second moments of the distribution P1, which we assume given here, right? So using our formulas for the coefficients A and B of the optimal transportation map tau star, we can finally express the squared Wasserstein distance between P1 and P2 analytically in terms of the first and second moments of these two distributions. So this reasoning culminates in this nice corollary of Brogniet's theorem. It says that if P2 is a positive semi-definite affine push forward of P1, then the squared 2 Wasserstein distance between P1 and P2 is given by the analytical formula that is shown here. So in 1990, Gelbrich proved a closely related corollary. And this result asserts that if P1 and P2 are arbitrary distributions, that means that P1 does not have to be an affine, positive semi-definite push forward of P1, then the same analytical formula we just derived provides, in fact, a lower bound on the squared Wasserstein distance of P1 and P2. In fact, Gelbrich shows that this formula coincides with the optimal value of a relaxation of Morph's optimal transport problem, where the push-forward distribution of P1 is allowed to differ from P2, but must have the exact same first and second moments as P2. So the optimal value for relaxation gives a lower bound. Okay, so now I've covered the basics of optimal transport, and now I'd like to turn to distributionally robust optimization. So here we study a decision problem under uncertainty, where some decision maker aims to minimize the expected value of an uncertainty affected loss function over all distributions x in some feasible set script x. However, the exact probability distribution p of the uncertain problem parameter xi is unobservable and only known to belong to some ambiguity set script p. So that's just a family of distributions. In this situation, an ambiguity-averse decision maker will minimize the worst case expected loss, where the worst case is evaluated with respect to all distributions in the ambiguity set. So this results in a distributionally robust optimization problem, which is in fact a zero-sum game between the decision maker who chooses x and some fictitious adversary. We often refer to it by a lack of better word as nature, who chooses p. So the ambiguity set in a distributional optimization problem is supposed to contain all probability distributions of xi that are consistent with the decision maker's prior statistical or perhaps also structural information about the uncertainty. And the popular idea is to define the ambiguity set as a Wasserstein ball of radius r around some nominal distribution p hat. This means that this ambiguity set contains all distributions supported on a given set capital Xi, whose pth Wasserstein distance from the nominal distribution p hat is at most equal to r. So the nominal distribution is usually constructed from statistical data, and it represents the decision maker's best guess for the unknown true distribution. In distributional robust optimization with a Wasserstein ambiguity set, however, there is an evil adversary, for example, some Faustian Mephisto, who can morph the distribution, this nominal distribution p hat, into some other shape at the finite transportation budget r, which is equal to the radius of the Wasserstein ball. Each time the adversary moves probability mass around, he has to pay a transportation cost that grows with the transportation distance. For example, moving a small mass over a certain distance, a small distance incurs a certain cost, while moving the same mass over a larger distance incurs a larger cost. The adversary may continue reshaping the normal distribution until the entire transportation budget is exhausted. And the example that I show here, the resulting reshaped distribution P, has a heavy right tail. Now, in any case, the adversary will try to morph the nominal distribution into some shape that is undesirable for the decision maker. So presumably a heavy right tail for many applications might be a bad thing for the decision maker. Okay, so in the following, I would like to highlight 4 striking benefits of distributional robust optimization models with Wasserstein ambiguity sets. A first main benefit is that distributional robust solutions underpromise and overdeliver. The histogram, the 2 histograms on this, sorry, the 4 histograms, the 2 charts on this slide, they visualize the in-sample and the out-of-sample risk of 10,000 independent replications of a mean CVAR portfolio selection problem, which involves 10 assets and 30 training samples. So on the left-hand side, we solved the problem with the sample average approximation, which replaces the unknown true asset return distribution with the empirical distribution, discrete empirical distribution over the 30 training samples. We observed that the sample average approximation, or SAA solution, overpromises in the sense that the in-sample risk is low, that's the green histogram, So it underdelivers, and the out-of-sample risk is, so it overpromises, and the out-of-sample risk, which is the red histogram, is high. So the solution underdelivers. On the right-hand side, we solved the problem with a Wasserstein distributional robust optimization approach, where we used a Wasserstein ball centered at the empirical distribution. And we observed that the resulting solution underpromises. That means the in-sample risk is now also high. And it actually over-delivers in the sense that the out-of-sample risk is low. And perhaps more importantly, the out-of-sample risk is what we really care about, is much better than that of the SAA solution. And it's much closer to the solution of the true stochastic optimization problem that we cannot, that we could only compute if we knew the true distribution, and which is visualized by the black dashed line here. So this kind of phenomenon we observe in many different applications. Now, a second striking benefit of Wasserstein distributional robust optimization is that the in-sample risk, and that is the worst case expected loss of a fixed decision, provides an upper confidence bound on the out-of-sample risk, which is the true expected loss. And the conservativeness of this upper bound can be controlled by tuning the radius R of the Wasserstein ball. Indeed, if R grows, then the in-sample risk increases, and if R shrinks, then the in-sample risk decreases. And in this situation, it is of interest to determine the smallest Wasserstein radius R that offers a bound, an upper bound with a certain prescribed confidence. So if the nominal distribution is defined as the empirical distribution over n training samples, and if the training samples live in a d-dimensional space, then a radius of the order n to the power -1/d guarantees that the Wasserstein ambiguity set contains the unknown true distribution p star with high probability. Now, this dimension dependence, however, is undesirable because it means that the conservativeness of the distributional robust model decreases only extremely slowly with the number of training samples. Luckily, however, one can also show that the dimension-independent Wasserstein radius of the order 1/√n is sufficient to construct confidence sets for the true minimizer and the true expected loss of the stochastic optimization problem at hand. Now, a third intriguing benefit of Wasserstein distributional robust optimization is that it provides a probabilistic justification of different commonly used regularization schemes. And to see this, let's fix the decision X, and let's define the Wasserstein ambiguity set with respect to the pth Wasserstein distance. Then one can show that the worst case expected loss of the fixed decision X is bounded above by the sum of the expected loss under the nominal distribution, that's just a nominal loss, plus p-1 different variation regularization terms, plus a Lipschitz regularization term. And the kth variation regularization term in this formula penalizes, in fact, some LQK norm of the tensor of kth order partial derivatives of the loss function with respect to the nominal with respect to psi under the nominal distribution. Yeah, and the Lipschitz regularization term penalizes the Lipschitz modulus of the tensor of pth order partial derivatives of the loss. So variation regularizers, such as the regularizers that penalize the gradients or the Hessian matrices of higher order partial derivatives, are successfully used in various applications of machine learning. For example, they appear in the adversarial training of neural networks, or in the stabilizing training of generative adversarial networks, or also in image recovery. And what we show here is that Wasserstein distributional robust optimization gives these heuristic regularization schemes a theoretical justification. If we define the Wasserstein ambiguity set with respect to the first Wasserstein distance, that is, if we set the exponent p to 1, then then the upper bound in the previous theorem reduces to the sum of the nominal expected loss and the R-fold multiple of the Lipschitz modulus of the loss function. And in fact, this upper bound becomes exact, so it becomes an identity, when the loss function is convex in Xi, and when the support set is in fact the whole space, so when there are no support constraints. And in particular, in distributionally robust regression or classification, the loss function is of a particular type. It can then be represented as L of X transpose Xi, where L is a univariate convex function, such as the hinge loss function in support vector machines. And in this case, the Lipschitz modulus of the loss function adopts a particularly simple form. That is, it equals the Lipschitz modulus of this univariate function L multiplied by the dual norm of X. And here, the dual norm is actually the norm that is dual to the norm that is used in the definition of the transportation cost function of the Wasserstein distance. So this result now offers a robustness interpretation for different classical regularization schemes in statistics and machine learning, such as the Lasso regularization and so on. Okay, so the fourth key benefit of Wasserstein distributional robust optimization is its computational tractability. And I think this is a very important one. A distributional robust optimization problem is essentially a zero-sum game between the decision maker and the adversary. And oftentimes you can indeed efficiently compute Nash strategies of the two decision makers. So the Nash strategy of the decision maker who chooses X can be computed by solving the primal distributional robust optimization problem, which is the one shown here, the standard DRO problem. And this problem is tractable when the nominal distribution P hat is discrete, and at the same time, the loss function can be expressed as the pointwise maximum of finitely many concave component functions. So in this case, one can use techniques from convex analysis to show that the primal distributional robust optimization problem is equivalent to a finite convex program whose size scales with the number of atoms of the nominal distribution and with the number of components of the piecewise concave loss function. Now, the Nash strategy of the adversary or nature can also be computed by solving a problem, in this case, the dual distributional robust optimization problem, which is shown here and which is obtained by just interchanging the order of minimization and maximization. So assuming again that the nominal distribution is discrete and that the loss function is piecewise concave, we can again prove that the dual distributional robust optimization problem is equivalent to some finite convex program, which is shown here. And I will not go into the details. However, I would like to emphasize that recently Mosaic have dedicated a tutorial paper and a Jupyter notebook to Wasserstein distributional robust optimization. And this Jupyter notebook is based on Mosaic's Fusion API for Python. And it makes it very easy for practitioners to solve the convex reformulations, these tractable convex reformulations of Wasserstein distributional robust optimization problems. So to showcase why the Nash strategy of the adversary is interesting to know, I would like to consider a particular example, that is a distributionally robust support vector machine problem, where Xi represents a feature label pair and X represents the gradient of a linear classifier. In this case, L of X and Xi can be thought of as the hinge loss of sample Xi under the classifier X. Now here, the Wasserstein ambiguity set is centered at the empirical distribution of the training samples, which are visualized on the slide. And the goal is, the goal of support vector machine, the support vector machine problem is to classify images of handwritten digits, for example, from the MNIST dataset. In this case, the feature vector would be a grayscale image with 784 pixels. So the distributional robust support vector machine problem acknowledges that the true distribution of the feature label pairs is very likely to differ from the empirical distribution. Thus, it minimizes the expected hinge loss not under the empirical distribution, but under some worst-case distribution in the Wasserstein ball, which is obtained by reshaping the empirical distribution at the finite transportation budget R. And it turns out that the adversary will actually move training samples around in the feature space. And in doing so, he will invent completely new training samples that were not present in the original training data set. So we can in fact construct a worst case distribution P star as one of the adversary's best responses to the optimal classifier X star. So that means we would have to solve the optimization problem that is shown on top left here on the slide. And the P star here that solves this maximization problem can be computed by solving some convex program. And again, this distribution P star will move probability mass from actual training samples, for example, the ones shown in the left column, the digits shown in the left column, to some adversarial examples, which are the digits shown in the right column. Now, these adversarial examples are invented by the adversary in the distributional robust optimization problem. And I would like to point out that they differ from the actual training samples just by a few seemingly random pixels. So it's a bit obscure what the adversary actually is doing here. However, alternatively, we could also construct a worst case distribution as a Nash strategy of the adversary. That is, as an optimal solution of the dual distributional robust optimization problem, which is shown on the top right of the slide. Now, this distribution P star can also be computed by solving a convex program, and this distribution also invents some adversarial examples. However, these adversarial examples are really deceptive. For example, the number 9 in the first line is ostensibly converted to a number 4, and this number 4 was actually not present in the original data set. So we conclude that the adversary's best response to the optimal classifier can perhaps deceive a machine, but not a human. However, the adversary's Nash strategy can even deceive a human. At least I'm deceived. So this probably happens because the Nash strategy aims to fool all possible classifiers and not only the optimal classifier X star. So it does something much more reasonable. Okay, so far we focused on, in fact, on Wasserstein ambiguity sets that contain distributions close to the discrete empirical distribution. However, working with the Wasserstein ball around the empirical distribution has two serious disadvantages. First, the size of the convex program equivalent to the distributional robust optimization problem scales with the number n of training samples. And this convex program is therefore difficult to solve for large n. Second, the statistical convergence of the empirical distribution to the true distribution suffers from a curse of dimensionality. Now, it turns out that both shortcomings can be mitigated by representing all distributions in the Wasserstein ball only by their first and second moments. So we thus can embed the Wasserstein ambiguity set, defined here in terms of the two Wasserstein distance, so where the transportation cost is squared Euclidean norm, in a larger Gelbrich ambiguity set, which contains all distributions whose first and second moments are close to the first and second moments of the empirical distribution in the sense of the inequality shown at the bottom here. So you remember Gelbrich's corollary from the beginning of the talk. So there we've seen that the expression on the left side of this inequality constitutes, in fact, a lower bound on the squared 2 Wasserstein distance. And this is the reason why the Gelbrich ambiguity set G indeed provides an outer approximation for the Wasserstein ambiguity set B. So the Gelbrich ambiguity set accounts only for statistical information about the first and second moments of the unknown probability distribution P star, and therefore it's invariably somewhat crude. So to enable a more nuanced description of distributional uncertainty, we intersected with a so-called stable ambiguity set script S, which captures any structural and non-statistical information. And here I would like to define the stable ambiguity set S as any family of distributions that is very abstractly closed under affine push forwards and under convolutions. What does it mean? Let me go back. So it means that if Xi1 has a distribution in the ambiguity set, then Xi2, defined as A times Xi1 plus B, the distribution, the push forward distribution P2 of Xi2 is also in the ambiguity set. On top of that, it means that if I have two distributions P1 and two distributions P1 and P2 that are both in the ambiguity set, then their convolution is also in the ambiguity set. And the convolution is, of course, just the distribution of the sum of Xi1 and Xi2 if Xi1 and Xi2 have distributions P1 and P2 and are mutually independent. So examples of stable ambiguity sets that satisfy these properties include the sets of all symmetric distributions, the set of all symmetric and linear unimodal distributions, the set of all log concave distributions, or more restrictively, the set of all Gaussian distributions. Now, to exemplify the merits of working with Gelbrich ambiguity sets, I would like to consider now the problem of measuring the risk of a portfolio of assets with respect to a given risk measure that has three important properties. It is translation invariant, scale invariant, as well as law invariant. So these are commonly used axioms that many risk measures that are commonly used do satisfy. For example, the law invariance just means that the risk of a random variable should only depend on the distribution of that random variable and not on the underlying probability space. It's something that is widely accepted. Now, if Xi here represents a vector of asset returns and X a portfolio weight vector, then minus Xi transpose X represents the portfolio loss, the negative portfolio return. So our goal here is to evaluate the worst case risk of the portfolio loss with respect to all distributions P that live in the intersection of some stable ambiguity set script S and the Gelbrich ambiguity set G sub R. Now, maybe surprisingly, one can show that this worst case risk coincides exactly with the sum of the nominal portfolio loss plus a term that is proportional to the nominal portfolio standard deviation plus an L2 regularization term. Now, remarkably, the worst case risk depends on the risk measure R and the stable ambiguity set script S only indirectly through a single constant alpha, which we term the standard risk coefficient. And this alpha is defined as the worst case risk of the standardized portfolio loss with respect to all asset return distributions in the stable ambiguity set script S with a fixed mean vector mu and a fixed covariance matrix sigma. So it's basically this formula here. Now, you can see that this formula on the right-hand side clearly depends on X as well as on mu and on sigma. However, we can prove by using the properties of the risk measure, most notably the law invariance, that alpha is in fact independent of these variables. So no matter what X, what mu, and what sigma we choose, this formula will always give us the same alpha. So it is indeed a constant. Moreover, what is nice is that this alpha can often be computed in closed form. And this is the case, for example, when the risk measure R represents the value at risk at some level beta. So the value at risk at level beta is actually nothing else than the leftmost 1 minus beta quantile of the loss distribution. In this situation, alpha is available analytically for various ambiguity sets, as you can see here. Now, in the special case when the stable ambiguity set comprises all distributions with finite second moments, then alpha is even available much more generally in closed form for all spectral risk measures, also for all risk measures that admit a Kuhn representation, and for all distortion risk measures. And these classes really cover the vast majority of all risk measures that are used in finance. So the theorem really shows that the worst case risk simply collapses to a Markowitz type mean standard deviation functional with an additional regularization term, irrespective of the actual risk measure that was used. And the size of the resulting convex optimization problem is independent of the number of training samples. So it can be solved extremely efficiently. Now, perhaps more generally, we can construct a conservative approximation for any Wasserstein distributional robust optimization problem by simply replacing the Wasserstein ambiguity set with the Gelbrich ambiguity set, which is a bigger set. Now, this approximation can be computationally attractive because the resulting upper bound can be computed by solving a convex program whose size is independent of the number of training samples. Moreover, the upper bound turns out to be exact in two important special cases. The first one is when the loss function happens to be quadratic in psi. It doesn't have to be convex, just any quadratic function. Or, that's the second case, if the stable ambiguity set is the set of all Gaussian distributions. So there are indeed several practically important Wasserstein distribution robust optimization problems with quadratic loss functions, which can be solved exactly and highly efficiently thanks to this Gelbrich trick. Examples include inverse covariance matrix estimation problems in high-dimensional statistics, also minimum mean square error estimation problems in signal processing and Kalman filtering, as well as regression problems with domain adaptation. These are problems where the out-of-sample data is generated from a different distribution than most of the in-sample data. Okay, so until now, we have mainly used ideas from optimal transport to formulate and solve distributional robust optimization problems. So in the last part of my talk, however, I would like to do the opposite and use ideas from distributional robust optimization to solve optimal transport problems. Specifically, I would like to address semi-discrete optimal transport problems, which seek the minimum cost of transforming a continuous distribution P into a discrete distribution Q. And we already know that such problems are sharply hard in general. Despite their hardness, however, they have several relevant applications. For example, they naturally arise in 3D morphing, in resource allocation, or also in the training of generative adversarial networks. And maybe more surprisingly, they can also be used as a tool to reconstruct the early state of the universe right after the Big Bang, based on measurements of the current locations and velocities of the galaxies in space. In addition, semi-discrete optimal transport problems, which compute distances, Wasserstein distances between continuous and discrete distributions, also emerge naturally in the simulation of incompressible fluids. And the beautiful simulation videos shown here are actually borrowed from Bruno Levy. Okay, so let us now study a generic semi-discrete optimal transport problem. Remember that P is a continuous distribution and Q is a discrete distribution. Now, it is well known that the primal optimal transport problem, which is shown here, admits a strong dual optimal transport problem, shown at the bottom, and the dual maximization problem optimizes over a vector phi of dual potentials. Now, the dimension n of this vector phi coincides with the number of atoms of the discrete distribution Q. The dual objective involves the expected value of a function psi c, which is defined as the pointwise maximum of the dual potentials adjusted by the cost function evaluated at the different atoms of the distribution Q. Now, this function is termed the C transform of phi, and by construction, it is a non-smooth function. It has some kinks. Now, in fact, the C transform can naturally be interpreted as the optimal value of a naive deterministic discrete choice model. Now, discrete choice theory was pioneered by Louis Thurstone and Nobel laureate Daniel McFadden, and it is routinely used in economics and psychology to predict the choices among finitely many discrete alternatives. Now, discrete choice models are usually stochastic because they are employed to predict the behavior of a population of different individuals. As not each individual has the exact same preferences, the utilities of different alternatives are thus modeled as random variables. And economists are then actually interested in predicting the probability that a random individual will choose a particular alternative. So this actually inspired us to add a random noise term, Zi, to the utility of the ith alternative and to compute the expected maximum utility. In fact, we assume here even that the joint distribution, theta, of the noise terms, the Zi's, is ambiguous, and we evaluate the best case expected utility, so the supremum, the expected utility across all distributions in a so-called Frechet ambiguity set, which we note by capital theta. Now, the Frechet ambiguity set contains all distributions with given margins. So all the noise terms, all the noise components follow some given distributions. However, the coupling of these marginal noise distributions is completely free. So that's where the ambiguity comes from. So in the following, we refer to the resulting best case expected utility, the optimal value of this discrete choice model, as the smooth C transform. And we note it by overline C, size C. So this terminology makes perfect sense. Indeed, adding noise to the utility values of a discrete choice model leads to a smoothing of the best case expected utility. And we now replace just the original C transform in the dual optimal transport problem with the smooth C transform. So this is an approximation, but we need an approximation because the semi-discrete optimal transport problem is a hard one. So using this smooth C transform instead of the original C transform amounts to a smoothing of the integrand in the objective function of the dual optimal transport problem. So the resulting smooth dual optimal transport problem is in fact closely related to a regularized version of the primal optimal transport problem. And here the regularization term penalizes some F divergence between the transportation plan pi, which is the decision variable in this optimal transport problem, and the independent coupling of the two distributions P and Q. Now, indeed, one can prove that the regularized primal and the smooth dual optimal transport problems are strong duals if the marginal distributions of the noise terms in the dual optimal transport problem are all constructed from some marginal generator capital F, which is basically a generalized univariate distribution function, provided that this F also determines the function small f in the F divergence penalty of the regularized primal optimal transport problem. So under these conditions, we have strong duality between the two approximate primal dual optimal transport problems. So this theorem unifies several existing regularization schemes in optimal transport and gives them a probabilistic interpretation. In that, our theorem motivates several new regularization schemes. For example, it implies that modeling the noise terms in the dual optimal transport problem using exponential distributions is equivalent to regularizing the primal optimal transport problem with a Kullback-Leibler divergence penalty. Similarly, modeling the noise terms using uniform or Pareto distributions amounts to regularizing the primal optimal transport problem with a chi-squared or a Zallis divergence penalty, respectively. And there are many more examples. So instead of solving the regularized primal, we propose here to solve the smooth dual optimal transport problem, which in fact is a standard stochastic optimization problem. We just maximize a function that involves the expected value of some decision-dependent function. Therefore, large problem instances can be solved with the stochastic gradient descent algorithm if we manage to construct unbiased stochastic gradients of this objective function. Interestingly, an unbiased stochastic gradient for the expected value of the smooth C transform is exactly given by the vector of optimal choice probabilities of the underlying discrete choice model. And this is super useful because we can now benefit from the rich literature on discrete choice theory, which provides many analytical formulas as well as efficient algorithms for computing optimal choice probabilities. So we use these optimal choice probabilities then in an average stochastic gradient descent algorithm, and we prove that this algorithm enjoys a 1/t convergence rate whenever the smooth C transform displays some generalized self-concordance property. And this is the case for optimal transport problems with Kullback-Leibler, chi-squared, or hyperbolic divergence regularization, among others. And we prove that the 1/t convergence rate even persists when there is only an inexact oracle for the optimal choice probabilities. So this is quite robust. Our theoretical convergence rate is consistent with the empirical convergence rate observed in experiments, and it significantly improves the 1 over square root t convergence rate for the unregularized optimal transport problem. So as a byproduct, we show that our algorithm improves on the state-of-the-art 1 over square root of t convergence rate for semi-discrete optimal transport problems with an entropic regularizers. These are problems that have been studied widely, but we give a new improved convergence analysis. So we may conclude that there is indeed merit in using ideas from distributionally robust optimization to solve optimal transport problems more efficiently. So this brings me to the end of my talk. In summary, what we have seen is that distributionally robust optimization problems with Wasserstein ambiguity sets centered at the empirical distribution are quite attractive for several reasons. They offer useful statistical performance guarantees. They are tractable in quite generic settings. They provide a probabilistic justification for various regularization schemes, and they lead to adversarial examples that do not only deceive computers, but can even deceive humans. Now, working with empirical distributions has the disadvantage that the convex reformulations of the distributional robust optimization problems grow with the sample size. And this challenge can be overcome by working with Gelbrich ambiguity sets, which focus on the first and second moments of the distributions in the Wasserstein ball. Now, working with Gelbrich ambiguity sets leads to conservative approximations that are independent of the sample size. However, these approximations are exact for quadratic loss functions or for ambiguity sets that contain only Gaussian distributions. Last but not least, we have seen that semi-discrete optimal transport problems are sharply hard, but can be addressed with fast stochastic gradient descent algorithms if we add noise to the transportation cost. So in fact, we have seen that adding noise to the transportation cost has two dual effects. On the one hand, it leads to a smoothing of the dual optimal transport problem. And on the other hand, it leads to a regularization of the primal optimal transport problem. So our analysis leads to a unification and internalization of various regularization schemes in optimal transport. Okay, so this is the end of my talk. Here is a list of references that I covered with more or less detail. And now I would like to thank you very much for your attention and look forward to a discussion or your questions.